really good water. Having really good water.
10 different types.
10 different types. Ah. You know, we
It's not one of those. Felix. Do you have like a multi-stick buzzer thing?
Not down here. Yeah. Okay, unplug something. Yeah.
My life now.
I hate that bag.
What? That Ralph thing. Oh, that video of Ralph now.
This looks so funny. Oh yeah. Oh.
I know. I'm exhausted just thinking about it. No, they're not comfortable. Oh, we did it in New York. So we have Ben said, which is good because she was spanking us, yelling at us, punishing us. She runs a tight cup.
I'm the one who suggests the lines and numbers protocols and breaking it out. Now you're getting. Like literally.
It's like you're talking, you've been talking about because you're talking about
Maybe she doesn't know what she's talking about. She makes it possible. So she's
yeah, it's great. People are just disgusting. That was great. Were you there? Yeah.
I was like, so I didn't see
I think we were playing lines.
Yeah, outside.
Hey.
Hello. World.
Hello.
Hello.
Is the microphone necessary? Can you hear me like this? Necessary. All right, we're just going to be like a few more minutes while Jake sets up here.
I'm going to need some people to get back away from the table. So
Everyone get back from the table.
everyone gets away from the table.
Jake's going to pick up.
Where do you want to start? Just on this
If you put the chairs in there.
Yeah.
Let's excuse me, I'm not very good with the microphone. I don't talk into it properly, so you know. Can we get any people in the window involved? You want to get involved? Hello. Yep.
I think you guys are right. They will be putting people on here. What's in your place? It's like leave a space all around the table. Jake, I might start here.
Jake, I might start.
Yeah, getting 2 seconds, nearly done.
2 people.
Oh, yeah. So everyone is probably going to have to stay a little bit back from this because we're going to be bringing some brewed coffee through here in about 10 minutes. We can do this, all right?
Maybe on that side as well. Do you need access to the other side?
Oh, I can really put it on the other side, but like once the coffee's here, everyone's probably going to be grouping around the table trying to get coffee. So it's all right to be just now, but once the coffee's there.
All right, should we talk about coffee? Water for coffee? Yeah? There you go.
All right, we'll start.
We'll start. All right, Jason. So yeah, hi, I'm Andrew. I'm working here at the bar, and I've got a lot of preparation for this little presentation, where I'm going to talk about the different things in water that are relative to coffee flavor, the way it extracts coffee, how we can test those things in the water, and also different ways in which we can make it, like filtration or adding the minerals afterwards, etc., etc. So yeah, and afterwards we're going to cook 10 different waters that I made, all very different, all with the same coffee. So it should be good, and I'm interested because it's not every day that I get to do this, and it'd be interesting to get like a collaborative opinion on what difference each aspect makes to the flavor. So yeah, these are some of the things we're going to look at. We got general hardness. General hardness is two things together. It's the calcium content and also the magnesium content in the water. We're also looking at pH. This stands for carbonate hardness. We're more interested in that aspect called alkalinity, which we can usually work out with this. pH, which is stands for the power of hydrogen, and this measures how basic or acidic the solution is. We'll go through a few things like chlorine, iron, and lead. Like obviously, lead is not very good in water. We're not going to focus on these too much. These are just other things that you find in water that's not very good. Like lead can kill you. It's not great, right? Carbon dioxide, how that can interact, and sodium. Okay, so first off, let's start off with water. As an entire thing, water is lots of minerals and particles together. Like it's a ratio of 2 hydrogen atoms to 1 oxygen, right? And this is how it always is if it's a pH of 7. As the pH goes up, you get less hydrogen in there, hence the name chirohydrogen. So, and what water is really unique is it's this word at the bottom, amphoterism molecule. It can react both as an acid and a base, which is quite unusual. And it can exist in its acidic form, it's hydronium, or its basic form, hydroxide. And it can dissociate as it gets warmer. It can have both these compounds in it, like hydroxide and hydronium. But if it's balanced out, then it can still maintain a pH of 7. So it can work like this, and it disassociates. So these are like 3 different properties of water. Hydronium on the left, H3O, with a positive, it's positively charged, and hydroxide on the right. If you add like the acids to the solution, it will give more hydronium. Basic compounds will give more hydroxides. For example, if we add CO2 to water, like you've heard of acidic rain, right? This is going to form an acid called carbonic acid. This is relative from when like we brew coffee that's too fresh. You know when it bubbles and you get like a really imbalanced flavored coffee? This is part of that. As well as creating an even extraction, it's going to create some of this carbonic acid. Carbon dioxide is released from like roasting, is going to get into the water. In the water and chlorine separately. If you put citric acid, which is actually a weak acid, into water, it maintains it like coffee, where that stands on there. We got right at the bottom, we got hydrochloric acid. Obviously, the lower the number, the more acidic the compound, the higher number, the more basic the compound. A really basic one would be sodium hydroxide. And we can see for every number on the pH scale, it becomes 10 times more. It's like logarithmic scale. So a pH of 0 compared to a pH of 7 is like 10 million times more acidic, which is quite a lot. And that's why from lemon juice number 2 to battery acid, which is going to like dissolve your arm, it's quite a lot, just for a small number of pH. As I said before, pH stands for the power of hydrogen, and it measures the amount of free hydrogen atoms in the water. This reading will vary greatly depending on the temperature. The higher the temperature, the higher the reading will be. So you always have to take that into account when you're taking a reading. When I make the water here, when I'm doing it, adding minerals, I always, even when I'm doing the ppm or a pH meter reading, I'm always going to read the temperature at the same time. It always depends on temperature. Going more into acids. strong acids, like I said before, sodium hydroxide, hydrochloric acid, they will dissociate in water. And weak acids don't, like citric acid. How's that relative to like a magnesium and calcium? So here, if you look on the top left, you can see we have magnesium in the green colored circle. This is going to be attracted to all these molecules. These are different like molecular structures of lactic acid, malic acid, citric acid, and quinic acid. What these things do, what calcium and magnesium they will do, they will form an intermolecular bond. So they're not going to like make a full bond, but they will like magnetize in a way, and they'll pull these compounds out of water. That's how it works. Let's get back to bubbles. So the alkalinity of a solution is the buffer. So we didn't really talk about this so far. Alkalinity is going to try and, if we're at pH 7, it's always going to pull the solution back to pH 7. If you put an acid in there, and it's got a high buffering capacity, it will always do that. It's made of a weak acid and a weak alkaloid. These are what buffers are. So if you put a strong acid in there, the weak alkaloid will automatically neutralize it. They're like working against each other. That makes sense. And vice versa. When we are measuring alkalinity, it's quite hard to do. So what we do, we measure the carbonate hardness here with the titration kit. Carbonate hardness is actually a measure of how much scale to build up on a machine. But usually, 9 times out of 10, it is equal to alkalinity, carbonate hardness. Why? Because it's always the lesser value of the general hardness for the alkalinity. So we kind of take this as our carbonate hardness whenever we're measuring. If you have a high carbonate hardness in coffee, the coffee is going to taste really flat and boring. That's because all these acids that you put in there are going to be buffered. So when you're making water or with your water, you need to have a nice balance of a slight bit of buffer that's going to neutralize any strong acids that are undesirable. As I said, strong acids are going to disassociate in water. So these things will take them out. Your weak acids are desirable. You want to keep those. So strong acids are going to react more, and they're going to, the alkalinity will attack the strong acids first, the one we don't want. So we want to get to a point where we're buffering those acids that we don't like, and then stop and leave good citric, malic, phosphoric acids behind. And then we get to drink that. Too much carbonate hardness, we're going to just kill everything. And hopefully we'll try that today. So when we're making the water, or each day we have to test the water here on bar, Jake's in charge of that. We're measuring the continuity tester and titration. I'm just going to talk briefly about a few other ways we can test, but these are the main two we are dealing with here. So continuity meters. They're using electricity and current to analyze the ppm of the water. The problem is that it will only measure the metals within the water. And this depends greatly on the water composition and temperature. Sometimes it's going to vary up to 50%. So it's really, really not a good measure if we want a really accurate measurement of what's in there. The reason we use these is it can tell you if something's different. If you're on the same day, or the temperature is very consistent, and your water changes by double, you know you've got a problem. It's just a quick measurement, nothing too profound in this measurement. So titration kits, these are a bit more interesting. So this gives a really good measurement of GH and KH, and they're pretty cheap. They're not reusable like a continuity meter, but yeah, not too expensive. We can measure the general hardness here, and what it is anyone seen any of these before? Like, let me test this. Yeah, yeah. We get a certain amount of test solution. They're quite good actually. Maybe I'll get one up here later and we'll look at it. And you add a certain amount. You have a titration solution, and you keep putting drops titration solution in the test solution, and all of a sudden, once it reaches buffering capacity with that pH, it will just suddenly change color, and you can convert the amount of drops that you put in the liquid to a ppm reading of that particular compound you're testing for. One con I found about this is the drop weight is quite inconsistent. You can improve the resolution by increasing your test solution size, but yeah, the drop size can vary from about, I think I've calculated about 75%. Also with your GH measurement, so the more sodium you have in the water, the more it will interact with your GH reading. Now this is an incredibly good way of measuring things in water. Yeah, but you will only find these in very like scientific labs. They basically split the light of the particle, and each thing has a signature, and you can measure parts per billion of certain molecular things in the water. Disadvantage is it costs, yeah, like I say, $10,000, $100,000, which you can't quite justify right now, and it cannot measure by carbon either. Everyone's probably seen this before, who works in coffee, I think. This is called a refractometer. This one particularly is used for measuring ppm, the percentage of dissolved solids in the water. The problem is with this, while it's very good for coffee, which has a very high content in the water, 1%, we're talking about a lot less than 1% when we're talking about the actual composition of the water. So the resolution of this device does not meet what we need in terms of what we got on the bar. This can cost like hundreds of euros. To get one that has a high enough resolution, you're talking again like 10,000. Methods of filtration. So we have activated charcoal filters. These are things that you will probably find in your Brita filters. These will remove things like chlorine. Chlorine has a very, and if you've ever been to the swimming baths, you know how that feels. They put lots of chlorine in there to keep it nice and clean. It's not smelling good, and it's not good if you want a cup of coffee that's perfect. So the charcoal filter is going to remove that aspect mainly. We have reverse osmosis that we use here on both our bars and in the lab. All our bars across the bar. This is probably the best, most practical way to filter the water. The problem is it's non-selective, so it's literally going to filter everything all at the same time out of the water. So if you have a high bicarbonate, like a high alkalinity, bicarbonate in the water, and a low general hardness, which is not usually desirable, usually you want a higher general hardness, the water will stay like that, but in less amount, if that makes sense. So this is non-selective. Also, to make it, most of these, they refilter the same water back in less percentage. So it almost distills the water. It like makes, ours here does it 7 ppm, so almost nothing in the water, and then it will add a certain amount back in of the previous water that it just filtered. Ion exchanges. It is quite interesting. When you pass the water through these ion exchanges, they will exchange the magnesium that goes, the incoming water will have magnesium in it, and will exchange it for potassium or sodium, depending on the ion exchanges that's in there. Very interesting. So I don't know how the guys are going on downstairs, and like I welcome any questions because I mean there's lots to talk about with water, but the guys are going to bring the water and these different types of water. And from what I just told you, maybe we can guess which bowl is matching this description. Do you think we can do that? Can I have a guess? So what would you expect the 200 ppm buffer coffee to taste like? Anyone guess?
Very flat in every regard.
Very flat in every regard. Okay. So if I made the water correctly, yes, it should. I hope so. And obviously the less buffer should be slightly flat, but not so much. And the magnesium at 330 ppm. What do you think? Too acidic. Actually, I'm interested in this because I never tried it that high. You know, people always say magnesium's really good in water. It's really good. Okay, so let's just put like 10,000 ppm worth of magnesium in. I don't know exactly how it's going to turn out, so I'm interested. Yeah, we're going to try distilled water as well. So, that should be interesting, no? Distilled water, what will happen? Will nothing get extracted? I doubt it. Tap water should have high bicarbonate here. I've tried it before, it's not too bad. But it's weird that I tried this, I have a masterclass that I do, and sometimes I use the reverse osmosis water and the tap water side by side. 9 times out of 10, the reverse osmosis water is the best. But every now and then, usually with like the low acidic Brazilian coffee, the tap water actually wins, which I find really interesting. And maybe that's, today we're just going to use the same coffee and brew it with different waters, but maybe a further experiment would be like different coffees with different waters as well. You can't really do that. It's a lot to ask if you're on bar and you're trying to retweak the reverse osmosis machine every time you down a new coffee. But I don't know. Jake was talking about seasonality when you hit Brazil season, maybe like crank it up a bit or something. I find it interesting. Does anyone have any questions so far? Let's make it like a discussion. So all of that.
What side do you want to do that? Right, so this side is labeled.
Guys, I have a question. Do you come to the effect what magnesium, calcium, hydrogen carbonate has, or do you discuss this, or do you give an input on this?
An input? What magnesium has? Yeah, so magnesium, I'll go back to this previous slide. Sorry, maybe I didn't get that quite. Yeah. So here we can see that the magnesium, let's look closely at this. Yeah, if we see this green dot up here, can everyone see that? That's a magnesium particle. And number 1, for example, is a lactic acid molecule, molecular structure. What this thing does, it's positively charged, magnesium ion. And at the back of these oxygen, the oxygen, the red, they're negatively charged. It's forming a intermolecular bond here. It's like a magnetic force. And when the water passes through with these bonds, it's going to pull that out of the coffee and into the water.
Yeah.
Does that kind of answer the question?
Yes. And the same with calcium, right?
Yeah, interesting. Calcium works exactly the same way, but it has slightly less binding capacity, so it's slightly less efficient. But what I find interesting is if you put more calcium in to offset that difference in binding capacity, I don't think it would taste exactly the same. The reason is if you put magnesium and calcium in water alone, the water will taste actually slightly different. And my own personal opinion, maybe we can try it today, is calcium gives a bit more body and a bit more rounded feeling. It's kind of chalky, right? But I think it'll be interesting today and get everyone's opinion, get everyone together and see if we can come to a group conclusion on that. But yeah, in terms of extraction, they're doing the same thing, but magnesium's more efficient. And that's why sometimes you get magnesium boosters, which is not a form of filtration, it's you're kind of putting things in the water that you want. So the magnesium boosters will boost the extraction, obviously, and I haven't seen really calcium boosters for coffee. Because it's just like a less efficient gas. Yeah.
I to discuss, but yeah.
Yeah, we can discuss as we go.
Yeah.
Pretty easy on that. Any other questions?
Can I go on?
Yeah, you can go on. We can have a conversation.
I do have a question. Hydrogen carbonate. This obviously hydrogen carbonate. Talk about this.
Carbonate.
HCO3.
HCO3. Carbonic acid.
It's a buffer.
Sodium bicarbonate. Did I say that? Maybe I got it wrong.
No.
Where was that? Which slide was that on?
I don't know. It's just maybe.
Did I say that?
Temporary hardness, I think. Page 4.
The carbon is isn't it HCO3? Hydrogen carbonate.
HCO3. I got
I think we have CaHO3 on this slide.
Yeah.
So
So you didn't discuss the concept of buffer yet.
the buffer. Oh, I did, didn't I? Let's have a look. Alkalinity. This one. Alkalinity.
Yeah.
Okay, alkalinity, as I say, is made up of a weak acid and a weak base. And it will always maintain the same pH. So your blood is like your body has a very good buffer system. If you drink lots of acid, well, not like strong acid, but if you kept drinking citric acid, you die if you had no buffering capacity. The body needs a very stable pH. So what acids and bases, they will counteract each other. You put an acid to a base and they will neutralize if they're equal strength. So does that answer the question as well?
No.
Probably a bit more.
It's fine.
No, it's okay.
Yeah. I just wanted to know what you know about like the buffering system. What effect it has on the extraction and taste.
So on taste, definitely, it's going to neutralize the acids, right? Because if you have the weak base in the buffer is going to, as soon as you put an acid near it, it will grab those hydrogen ions and neutralize them. Like the power of hydrogen, it's all about how many hydrogen ions you have there, and the buffer is going to soak them up. It's negatively charged, like hydroxide is a base, right? If you look at the bottom right, hydroxide is a base. Let's just say, so if a hydrogen ion goes near that, it's got 3 negative charges to go, and it's just going to suck it up. And then a buffer has that concept inside it. Any other questions? Did I answer everyone's? I'm not a scientist. This took me quite a lot of reading. I think it's all correct. Yes. But yeah, it's a really complicated subject, and I didn't know where to really stop. Because you keep reading on and on and on, and then you end up like quantum physics, and I thought like it's too far. So yeah, we got it all set up already. Are we ready to cut? No? No one's cut? Yeah, all right, good. Good, so if you want to grab yourselves a beaker or a spit cup and a spoon, can you return the spoons, please? All souvenirs. And we'll have about 10 minutes of this. I hope they're all roughly the same temperature. They should all be roughly the same temperature now, but let's have a look at the sheet. Okay, so we're just twisting the numbers around now, and you can see we've got 1 to 10 on the left, my left, and then on the other side, we're going to label these A to So, on this little sheet here, you can write your tasting notes, your thoughts, your dreams on there. Whatever you think about the coffee, in this little note section. And then in the type section, let's try and just think if it's a high magnesium content, low magnesium content. If you think it's got big buffering capacity, if you think it's barely in tap water, just have a complete guess and see what you think. And then the matching bowl on the far right hand side, we're going to try and match the balls on this side to the balls on that side, because they should be mixed up. Are they mixed up, Maddie?
I have no idea what anything is on this side.
Did Jake do it? What did you do? But you like mix them up, right? Alright, cool, yeah. So, dig in. Oh, does everyone know how to cook coffee? Cup coffee? No? This lady here is going to show you how. Tommy, where's he? Tommy? Oh, there you go. So, Tommy, you're going to show everyone how to cook. Please demonstrate.
You use a very small spoon and you take the
No,
bowl when you're done.
ignore him. Someone said something. Anna?
And you slurp so that you mix it with air, and then you spit it out. Unless you want to get high.
Yes, please wash your spoon. You probably want a bigger spoon than Tommy's. Maybe get a big one. Get a nice slurp. We're doing this to get our olfactory system going. It's going to spray up our nasal passage and give us all those like aromas and things. No. Don't all jump in at once.
Enter. What coffee is this?
By the way, for those of you who know our coffees, it's the new Placenta 1355 from Brazil. By the way, we're all going to we've got beers in the fridge. If anyone wants to hang around afterwards and talk about coffee and drink beer, you can do that. Yeah.
so you got to get the type of thing no.
Is anyone else say that it's good? Anyone think it's good?
Shortly, moving around with a clockwise direction. Let's go around in a clockwise direction. Can everyone move?
Yeah, but Abraham, clockwise. No. It's okay, anti-clockwise.
Oh, right, sorry. Everyone go anti-clockwise direction. And go very slowly, don't stop. And the process is going to go cold. I don't know. We like yours.